Okay, excellent. So proof of Taylor's theorem. And I do want to do the one variable case because it really is the more interesting one of the two in terms of the proof. So, what is the result?
Sir, recording, sir.
Yes, thank you for the reminder. I will start.
Recording in progress.
All right. So you have seen the proof of this theorem last semester, so this should not be new. But let's try to motivate how the construction goes, right? The one variable case. So here is the hypothesis. F is a function from, let's say, a real valued function from a closed interval. And the properties are that F is continuous, it has a derivative which is continuous and all the way up until a certain level. And the next derivative exists. So more precisely, let us say that F, which is F0, 1, F prime, which is we call F1, F double prime, which is F2, and so on and so forth, up until a certain stage. So let us say up to M minus 1 are continuous on this closed interval. In particular, they exist, but not only do they exist, they are continuous. And the next one, the mth one, so it exists. Well, we actually need to have it only on the open interval, no? So, of course, in practice, what happens is that very often everything exists everywhere, right? At least for nice functions. Then, and let us say that suppose we are given 2 points S and T in A and B. Then there exists a point theta strictly between S and T. Now, this slightly awkward way of writing is because I do not want to assume that S is less than T or the other way, such that, so my reference point is S, and I'm going to use the values of the derivative, the values of the function, its derivative, and so on and so forth, to approximate T using all of this data at S. So the familiar thing such that f of T equals f of S all the way up to f to the m minus 1th derivative of f evaluated at S divided by m minus 1 factorial times T minus 1 S to the power m minus 1. And then the final term, which is the mth derivative, almost the same thing, but with a major difference, times T minus S to the power m, but evaluated at this point theta. So that's the error term. Okay. So proof. So the idea is that I am going to use this polynomial expression so this is a certain I can think of this as a certain polynomial evaluated at the point t. Okay, so this is equal to p of t, where p of x is, I use the exact same expression except I replace all the t's with the variable s. So what is this? F of s plus f prime of s times x minus s plus f double prime of s times x minus s the whole square divided by 2 factorial, and so on until the m minus 1th derivative of f evaluated at s divided by m minus 1 factorial. So notice that everything that is written in the front, it's just a constant. Okay, so all of these are just numbers times x minus s to the m minus 1. Okay, very good. So what is the point of this? The point is that if I calculate this, if I evaluate this polynomial at s, well, only the first term survives. So I get f of s. But what about p prime of s? Well, the first term dies because it's a constant. Then all the terms from 2 power 2 onwards also die when I evaluate at s, because the power of x minus s is still staying in them. And I pick up only f prime of f, s. The second derivative of s, the second derivative of p at s, it also matches that of f, and all the way up to the m minus 1th derivative of the polynomial, and the function are equal at the point s. Okay. And what about the mth derivative? What about the mth derivative of p? Come on, this is
0.
And not only is it 0 at s, it is identically 0. Okay. So the idea is that I like polynomial functions. Next to linear functions, they are the simplest functions. So this function f may be quite complicated, but in the vicinity of s, I want to approximate it with a simpler function to as much accuracy as I can. And the accuracy here is imposed by means of the conditions about derivatives. Namely, the derivatives of f and the derivative of this polynomial should match at s. That is how, that is at least my heuristics. That's how I hope that this polynomial will match the function well in a neighborhood near s. Okay. So let's look at what we want to prove. What we want to prove is that f of t is really equal to p of t plus some error term. And this error term is supposed to be of a specific type. So how am I going to try to get this error? And the idea is that I am going to apply the mean value theorem. So here it is slightly unmotivated in the sense that I am pulling this as a rabbit out of the hat, sort of after the fact. But mean value theorem is a mainstay of calculus, so we just use this all the time. So here is the idea. So, okay. So if I define g of x to be the difference between the function f and the polynomial, then I have, what do I have? G of s and g prime of s, g double prime of s, all the way up to the m minus 1 derivatives of s of g at s are 0, because it's all these derivatives are just the differences between the derivatives of the corresponding derivative of f and that of p. All right, so easy and nice. So I want to use, and I can use, use the mean value theorem for g on Okay, so here G prime, G double prime, all the way up to notice that by hypothesis, a polynomial has all derivatives everywhere, and f has the requisite derivatives, and they are continuous on this closed interval. So for each one of these, I can use the hypothesis satisfied. Okay, so the way I want to use this is that sorry, not on AB. On the on between S and B. Oops. The point though is that I would like to be able to use Rolle's theorem. So yes, you see, this is a bit after the fact, but let me still plow on and say what I want to say. If, and this is a very big if here. Notice what happens. If g of t is equal to 0, then remember at s, all of the value, the derivative, all the way up to m minus 1's derivatives, they're all 0. So what do I get then? In fact, Rolle's theorem applies. What do I get? I get some number between s and t such that what happens? So I'm going to call this theta 1 in, okay, so I cannot really say, okay, let me just say that I cannot write s comma t because s may not be smaller than t. So it's really the interval from s to t or t to s. So we will just go from a to. But here, by Rolle's theorem, if I apply it on the interval that extends, that has endpoints s and t, I will get theta 1 between s and t such that g prime of theta 1 is equal to 0. And now I have a cascade process. So here is the issue. Now, g prime of theta 1 is equal to 0 and g prime of s equal to 0. So what do I get? Remember, theta 1 is between s and t. So now I can apply Rolle's theorem to the function g prime on the interval from s to theta 1, or the other way around, depending on which one is smaller. And what do I get?
So there exists a theta 2 between theta 1 and s such that g double prime of theta 2 is equal to 0.
Exactly. And theta 1 such that g double prime of theta 2 is equal to 0. And now it's a chain reaction. Now g double prime of so this gives me theta 3 between And this is strictly between S and theta 2, such that this S and T, and then the such that is a poor combination. All right, we are adults, we can deal with it. Such that the third derivative of G at theta 3 is equal to 0, and so on. Okay. So this is all very good, and I will get a theta n. And so on till we get theta n with Gn of theta n is equal to 0. And we are all still in the air at the moment, because I really do not really have that G of t equal to 0. G of t can be anything. So let us see what G of t is. So at present, well, let's write down what G of t is. G of t is equal to f of t minus p of t. Is there any earthly reason for this to be 0? The answer is no, right? I mean, this polynomial, I really have no idea what the original function is. But now here comes the point. All of everything that I have done before, I can preserve if I adjust this function by something with what properties. Remember what I needed. What I needed was, I needed the derivatives of G to be 0, the first m minus 1 derivatives of G to be 0 at S. I have already achieved that. I do not want to disturb that property. But I want to change the value of G at a certain point. So what do I do? So what do I get to do? What can I do? So is there, okay, so is there any way in which I can add something to a function without changing its derivative, without changing, let's say, its double derivative, let's just say at 0. Is there anything that I can add to a function without changing its double derivative at 0?
Any linear polynomial?
Right. Well, okay. So, right. So, see, the point is, if I take a polynomial, then an eventually its derivatives vanish. So actually, let's see carefully, because the way we want to use this is the other way around. Okay. See, for example, if I add a linear polynomial, okay, so okay, so here, what kind of polynomial can I add to G of S, which will keep all the nice properties that I want, but it will adjust the value to a suitable value at t. So here is the idea. Adjust G of X. Remember, G of t is a constant, G of X. I can adjust G of X by constant times a power of X minus S to some power. Without affecting G of S equals G prime of S equals what is that? G to the n minus 1 evaluated at S equal to 0. And you see, so do I want high power of x minus s here or low power of x minus s?
High power.
Yeah, because you see, if I see, the point is I want to match this at s. So if I take high power, then even after taking m minus 1 derivative, some power of x minus s will be left. So if I plug in s into that for x, I will still get 0. So by constant, and the minimum power of x minus s that will work is going to be precisely m. You see, why will it not work if I just add something times x? The point is then if I take the first derivative, then it is going to just pick up the constant. And there is no way for me to cancel that constant because plugging in s is not going to do anything. Similarly, if I add an x minus s the whole square term, then it will work very well with the first derivative and certainly from third derivative onwards, but it will not work well with the second derivative, right? Because x minus s the whole square, its second derivative, is going to be a constant,
Yes, sir, that makes sense.
right? So this is the thing. So constant times x minus s to the power of m. And now you see this constant times x minus s to the power of m, I can make this quantity have any value that I like at any number by adjusting the constant, correct? So remember what it is that we want. We want to adjust t in such a way that all of these nice derivatives that I have matched at s, I don't want them to get affected. So that I have done. But I also want this, correct? I want this. So what do? I just plug in, I just adjust the constant multiplying this high degree term. So adjust. So let's give this constant a name. Adjust constant m to make g of t equal to 0. So let us see what needs to happen. So what I want is, so my new g is going to be f. So let's say g of x minus, f of x minus p of x minus m times x minus s to the m. So what is g of t? F of t minus p of t minus m times what? T minus s to the small m. And if I want this to be 0, then m, whatever m turns out to be, that is the value that I want. So let's just see this. So what is this? Let's just take m to the other side. So I will get f of t minus p of t divided by t minus s to. Okay. Everything works now, and everything is beautiful. So I get so I just have to now gather the final result. So what is it that we got finally? Remember, this is the thing that we got. Our final result was this. So what is the nth derivative of g at theta? And remember, theta, and I have taken that to be theta. So we get the nth derivative of g at theta. And remember, this is supposed to be 0. I have gotten that. But I can just look at the formula. So what is that? Well, let's just do this. This is the nth derivative of f at theta. Oh, sorry, I have changed m to n. Mth derivative of f at theta minus mth derivative of p at theta. But what is that? Remember what p was? P was a polynomial of degree m minus 1. So its mth derivative is 0 identical. So I get minus 0. And minus what? Look at the formula for g of x. What do I get? Come on. Oh, I'm over time. So let's finish this quickly.
M times M factorial. I think.
Yeah. So it gives me
Yeah, capital M times small m factorial.
small m factorial times capital M. Poor choice of notation. Sorry about that. And so finally I simply get. So you see there are two expressions for m. One is the expression that I have written here, and then this expression gives me that m is equal to the small mth derivative of f at theta divided by m factorial. So I'm already over time, so I'll just say equate two expressions for m and solve for f of t to get the result. All right. So very nice proof. So we are out of time. On Wednesday, I will do the multivariable theorem. But remember, we really did the proof of this. The only thing that is left for you to do is to correctly apply the chain rule. So let me end with saying this. So exercise. Carry out proof of multivariable Taylors by G sketched in last class, specifically using chain rule to calculate f of a plus ph. So this is the first exercise. And then this last exercise is really something. So in fact, you know what? Let me end the class and then I will state the last exercise for only those people who are interested. And we will take it up next time.
Recording stopped.
Okay. And so feel free to leave, as always, feel free to leave anytime. On Wednesday and Friday, I'm not going to be doing any new theory other than just doing this proof. We wrote down a complicated formula, complicated looking formula for Taylor's theorem in multiple variables, right? And there were some questions and comments last time which sort of hinted that at least the first term in the Taylor's in the one variable Taylor formula. So let's look at the first term in the one variable Taylor formula. So think of S as A and T minus S as H. Right. So the first term is really F prime of S times H. We saw that this first term still made sense in the multivariable situation, where I am multiplying, taking, let's say, the dot product of the vector H with the gradient, or even more basic, just evaluating the derivative on the vector, because the derivative will be a row matrix and the vector will be a column matrix. So that term made sense. Then somebody said, in fact, let me just go to the previous class. Right, so look at this. Look at this, the one variable situation. Now somebody said that the third term here, so let me just, somebody made an interesting observation that I can think of this second degree term by putting an H on one side and H transpose on the other side. And then this F double prime of A will be a matrix. In fact, it will be a square matrix. So on one side, so on the right hand side, I can multiply by a column vector, and on the left hand side, I can multiply by the row vector corresponding to it. Just take the transpose of H. Right? We will see this later on in the context of optimization. So this term can also be thought of without, without resorting to all the blood that comes out, all the blood that you see over here. So this brings a natural question. Is there a way to make sense of this one variable formula in the multivariable situation exactly as it stands? So I hope the question is clear. And the answer is yes. So let me write that as a problem. And you can try to see this. For F of A plus H, one variable Taylor formula for stays valid in the multivariable case. A small exclamation mark, especially if you like formalism. If you don't like formalism, then that's okay. Then maybe delete the exclamation mark. So of course, the key thing is in what sense. So how to make sense of this, of the expressions. So remember what the expressions were. Expressions were something like f, the kth derivative of f evaluated at k divided by k factorial times h to the k. As stated, it makes no sense because this is a number. But in the multivariable situation, what kind of gadget is this f to the power k, the kth derivative of f at k? It's some complicated thing, no? Kth derivative, when I take kth derivative at a point, then it is a linear map from Rm, taking values in linear maps from Rm So idea. So that is one problem, that this is a complicated gadget. It's some very large matrix. If you think of it, it's a very large matrix. That is one difficulty. And other difficulty is, what does h to the k mean? H is a vector. What does it mean to multiply it with itself k times? So in the two variable, in the quadratic case, remember what we could do. We could put h on one side and h transpose on the other side of the matrix. But for higher degree terms, something like this is not going to work. So here is the idea that I'll give you and then stop. Realize that so let us say more generally, for f from Rn to Rl, let's say. F double prime of A can be thought of. So remember, f double prime of A is really a map from where to where? So let me which is a linear map from where to where?
Rn to the space of linear maps from
Rn to
Rn to Rn.
Rn to Rl, right? Can be thought of as a bilinear map. From Rn cross Rn to Rn. Similarly, f triple prime of A is essentially, or not essentially, let's use a better word, is equivalently what kind of map from where to where?